The world of artificial intelligence hardware just experienced a groundbreaking revolution. Cornell University research has successfully developed the world's first microwave brain chip, a revolutionary low-power silicon microprocessor that completely reimagines how computers think and process information. This innovative microprocessor represents a fundamental shift from traditional digital computing. Instead of relying on conventional digital logic, this cutting edge technology harnesses the power of microwave physics to create a new paradigm in AI processing.
Yeah.
What's going on here, John?
Yeah. So this new chip, think of it like it processes information more like how our brains work. So everything happens all at once. So in parallel, using natural physics of microwaves, and instead of converting radio signals to digital data, then processing them, this chip can understand and respond to radio signals directly while they're still in microwave form. It's so fast, it can operate at tens of gigahertz. I don't know how fast the chips are now, but I remember like 5 gigahertz, things like that. So I'm not sure they got much faster. They just got more efficient, I think. But that's billions of cycles per second. And that's so much faster than most digital processors now. It also uses less than 200 milliwatts of power, which is about the same as a bright LED light bulb. To put this into perspective, a typical smartphone processor uses several watts and can't directly process radio signals at these speeds. And what's crazy about this all is it can do multiple jobs at once. So it can decode radio signals, track radar targets, classify data patterns, and even detect security threats in wireless communications all in real time. It's like having like this super powered antenna that can also think about what it's receiving, which I think is really cool. And we're talking applications here, right? They're endless. So you can have a smartwatch that can process AI locally without connecting to the cloud. You can have security systems that can instantly detect unusual radio activity, or radar systems that can identify and track multiple objects simultaneously without massive computing power. Like you said, it's a fundamental departure from neural network implementations, which is super cool. And I'm curious to get to know what your thoughts on this are, Craig, because this is cool.
This is really cool. And as you look into it, it's backed by DARPA, which isn't a surprise because this looks like it has military applications all over the place. Specifically, when we talk about, I think last week we talked about the infrared countermeasures from the Chinese AI, where they're scanning on the pilot and the plane at such a fast rate they can determine what the pilot's going to do before he's going to do it and counter it.
Yeah.
So when you now say, okay, we got these faster, lower powered, on the fly that can react faster and faster and faster, we're going to see more and more military applications. But I'd like to see these things in cars for collision detection, among other things. So they can communicate with each other a little bit better from a car-to-car communication point of view. So, that traffic and whatnot can go better. I think there's so many applications for this type of technology that it's going to be interesting to see if this actually takes off or not. Like right now, they have some problems with errors. Like it's only 88% accurate before we start needing error correction and whatnot. But this is early days. And, this is microwave. What other technologies out there, once you start building wave technology into chips where it's communicating at this different level, what else could we do with this?
Yeah. And it's like, so the other thing too, it's very sensitive. So it requires careful calibration. But again, we're talking a prototype design, right? That has actually been tested. And this is awesome because up until now, we've been converting these analog signals to digital signals, right? And I love that the team took the approach of, well, why don't we just work in the analog space? And it makes so much sense when you actually think about it, because you're eliminating 2 steps. You're eliminating the conversion from analog to digital and digital to analog, right?
Yeah, and building computation and communication in one chip dissolves traditional hardware boundaries that, all of a sudden things become so much easier. Chips versatility spans radio decoding, radar tracking, anomaly detection applications. Microwave interference enables massively parallel real-time computations with low energy demand. This might allow for way more multitasking than we have. And we're talking about, again, edge devices potentially, so they can react in real time without needing a cloud. So anything that needs to make decisions on the fly without checking back, this kind of thing could take advantage of.
Yeah. No, it's cool. And the other thing that we didn't touch on, it's built on standard CMOS, which means it can scale with existing semiconductor manufacturing, unlike these other exotic neuromorphic approaches, which require specialized fabrication. So this has the potential to scale and commercialize pretty quick.
Yeah, well,
yeah.
But
if they can address the sensitivity and the error, right?
Yeah, and it's definitely fewer specialized chips overall will reduce complexity and cost and points of failure. They just have to ramp up, in some degree to get this integrated. And I don't know what this means from what kind of operating system will be needed to run this, but I'm sure that just comes along with the system.
Yeah, exactly. Yeah. So there's multiple, for the challenges, they see multiple pathways for improving accuracy and scalability. So what they're thinking about doing is adding more tunable parameters, reducing on-chip component counts, and connecting arrays of MNNs for richer spectral features. And so they also are envisioning training methods. So those will jointly optimize the slow control sequences and the back-end model, which could potentially enable a kind of a waveband agnostic neural processor, which could span from millimeter wave frequencies down to narrowband communications, which is pretty friggin' cool.
Absolutely. We'd love to hear what you think about this microwave brain chip and its potential to reshape AI hardware. Let us know what you think. And remember to like and subscribe and leave a comment below. So, what do you got going on, John?
Yeah, so coming out end of September, definitely gearing up for Elevate. I know you're a partner with Elevate, aren't you, Craig?
Oh yeah, absolutely. So definitely we'll be doing something during the Elevate a week, probably a Flowgrammer event, if nothing else. They're a partner of ours. Definitely go out and check it out. There's a lot of great events going on related to Elevate. I swear I said great events, sessions. Program, check out their schedule, check out all the different lines of programs and stuff. There's always good things there. So definitely go check out Elevate and check out Toronto Starts for our startup drinks, our startup investor drinks, and our Flowgrammer events where we help people learn how to automate things in their business. And John, if people need funding, where do they go?
Yeah, come find me on LinkedIn. I just posted some news about the Shred program, but come find me on LinkedIn. Send me a message and we'll talk and see if it makes sense to find some non-dilutive funding for you.
Really appreciate everyone taking their time to watch or listen to this week. We'll see you again soon.
Thank you.